University of Chieti Pescara in Italy. And today, Professor Valentino will talk about 3D printing construction, 3D printing construction and robotics for new structures and repair in the digital age. So thank you very much, Professor Valentino. The floor is yours.
Thank you for the presentation. Can you see my screen? Can you hear me?
Yes.
Okay, perfect. We can start.
We can hear you.
So first of all, a little bit of context for what concerns 3D construction printing. In the last year, if we look at the most important report of the economic consulting agency, all the agency agree that the market is growing very fast, the market related to the 3D construction printing. Specifically, if we compare a little bit of data, we can state that the prevision is that the 3D construction printing market that reached 3.42 billion of US dollar in the 2024 is projected to reach more than 100 billion dollar by the 2032. So this is a very interesting prevision. And this is why all the company are starting developing R&D department to study 3D printing, to develop a new 3D printing technology, or to apply 3D printing technology in the construction site. This is an overview of the most important actors that are working in the 3D construction printing. And today we will focus on one of the most important technology that is built from COBOD. These are data from the 2024, and we can see that the COBOD 2, that is the 3D printer of COBOD, is the most used, is one of the most used in the world. This is important. Why? Because in our project, and here I introduce the ARIES project. ARIES is the funding program, and our project is named Safe 3D Printed Concrete Structure. So in this project, we decided to investigate the most important 3D construction printing techniques and technology, so the COBOD. The idea is that all over the world, a lot of 3D printing have been under construction and are being used, but the real seismic performances of this construction are not well investigated, at least before the proposal of our project. Indeed, in the academic sector, are there a lot of preliminary characterization tests of the material, but no one tried to study the effective behavior of a 3D printed unit after real seismic and dynamic force. So we propose for the first time the analysis of a real scale structure analyzed on a shake table. To the left, you can see a short video of the technology. So this is the COBOD machine. This is interesting because you can print also concrete with some aggregates of 2 centimeters of diameter. So this is quite a large aggregate if compared with other technology. In addition, we investigated the construction techniques that are being used in the real sector. For example, here you can see a prototype of a construction built with this technology from HTL Tech, a partner of our project. And typically, these constructions are built with 2 walls that constitute the envelope, and inside the wall, the company are including also insulation material. Are there also some important structural detail that I will show in the next slide. From this, one important thing is this change of color. So please remember this kind of situation because it's very important for the structural performance. This happens when you stop print in one day and you start print in the day after. So this is a cold joint that is difficult to avoid because on the other hand you should have workers that work full time. In addition, this kind of joint can happen also for a momentary issue of the 3D printer. Sometimes happen. And so also this the position of this cold joint is not we cannot forecast all the time the position because if the machine have a small problem or if the concrete have a problem in the pumping system, we need to stop the printer and this create a cold joint. Okay, so this is the view of the building after the finishes. And this is a construction typology that is already being used in the north of Dublin, because this is HTL Tech, that is a company that work in this area. So this construction technology is changing the paradigm of construction, because this new typology of construction is not similar with steel, or is not masonry construction, and is not similar to the classical reinforced concrete frame structure. This is something new. Indeed, we have orthotropic material that is related to the process of the creation of walls layer by layer. We have new construction detail. For example, here you can see an intel that is used to create opening. We also have different reinforcement. You can see here that we put this kind of light reinforcement to avoid the collapses of the wall during the printer. And this can be also helpful to make the two walls collaborative in the entire envelope. And finally, we have the cold joint. So you can see here what happened when you stop the printer and you start again after a few hours or the day after. Typically in the construction practice, company use some bonding primer to increase the connection of this cold joint, but I can say that it is not sufficient to have the same characteristic of the rest of the construction. So we decided to investigate this problem in a 4-step procedure. First of all, preliminary test to analyze the orthotropic nature of the material. We used the preliminary test to calibrate a numerical model, and after we designed the final test by considering the foundation level, the connection with the shaking table, and also the dimension of the specimen. And finally, we had the final full shake table test. This project is made in collaboration with the University of Porto, ASDEA Software, my university, University d'Annunzio of Chieti Pescara, University of Bristol that hosted the final shaking table test, and HTL Tech, that is the company that provided us the COBOD technology. So first of all, first step is the characterization of the material. Since we have an orthotropic material, we had a lot of tests. So basically we printed a wall and we colored samples in different direction, and the same thing is made for SOCAT that has been used for bending test and also tensile test. Finally, so you can see here the overview of the test that we made, some picture, and this is one of the most important that had been very interesting for the calibration of the numerical model, a diagonal shear test to try to understand the behavior of this configuration. So the next step was the calibration of the numerical model. We developed two different typology of numerical modeling. One by considering a layered model, so we model every single layer with the interface, and another version of the numerical simulation with an homogenized material. So in this case, the orthotropic nature is included in the information that we use to build the numerical model. The numerical model is made with STKO, that is a software that is developed by ASDEA. The result was very similar, and so we decided to use the homogenized model because this is quick to be achieved, and also the computational cost is lower than the layered model. The result is almost the same. And you can see here that the cracks that occur in the diagonal shear test can be really can be simulated very well in the numerical simulation. The third step was the design of the printed unit to be tested on the shake table. So we developed a parametric model, and you can see that with this parametric model we can change a lot of geometrical configuration of our construction. In particular, also the position, the dimension of the opening, the radius of the corner, all the parameters that can be important for the structural performances. This was very important to achieve the final configuration of the test, because we, with this script, we was able to, in a very fast way, to generate a 3D model to be analyzed in the FEM software. So after an iterative test of exporting of the geometry, adjusting of parameters, and simulation, we reached this final configuration. Since our goal was to investigate the seismic performance of the structure and not the connection with the soil, we decided to connect perfectly the construction with a steel ring beam that has been directly connected with the shake table. In this way, we started printing directly in the laboratory. So here we are in the Softy Lab, the laboratory of Bristol, the structural laboratory of Bristol. And you can see that we used exactly the same construction techniques that is used in the real world. You can see also here other reinforcement that can be used typically in the construction site to reinforce the opening. So after this, we used a lot of sensor, camera, accelerometers, but also sensors to identify the formation of a lot of different components of the construction. So you can see here a lot of sensor located around the structure, and we started the test. If we wait a few seconds and we go to the end of the video, you can see exactly the moment where a huge failure occurred. In particular, we can jump to the end. If you look here, you can see that all the upper part have been detached from the rest of the structure. Here, you can see here a huge crack, and another crack occur in this position. So here you can see what happened during the test. This is the upper crack, and here you can see a lower crack, one horizontal and some diagonal crack that reached the opening. Why this is interesting? Because this has been exactly, the cracks occur exactly in the position of the cold joint. So we can state that after this test, we demonstrated for the first time the importance of the cold joint if compared with the opening. In the future research, we will complete the analysis of all the numerical results of the test that have been concluded in a few months ago, and so we will be able to disseminate in the scientific community all the numerical result of the modeling, the calibration of the model, and all the numerical result of this kind of test. Okay, I just want also to introduce another project that is not properly 3D printing, but is strictly related with the robotic and of this kind of tools in the construction sector. This project is named Masonry Surgeon Bot, is a FISA project funded by the Italian Ministry of Research in collaboration with a local company. This is interesting because we are building a robot that is able to operate like a surgeon on the masonry to reinforce the existing construction. So we will develop a fiber reinforcement system that will be extruded or included directly inside the mortar joint to reproduce a modern version of the reticulatus intervention. So here you can see the robot of the company and the complexity of the end effector that place the fibers. And in our project, we are starting developing all the automatization system for the robot. So the robot will be able to recognize, as you can see here, the robot will be able to 3D scan the masonry, identify the mortar joint, and will be able to operate directly inside the mortar joint. This is just a simulation, but you can see in our laboratory that we are starting working with the robot to try to make the robot safety during the operation. So you can see some obstacle here, and you can see the robot that can avoid the obstacle during the toolpath. And here you can see the toolpath that is fully generated with artificial intelligence in combination with a Python script and Grasshopper. So the combination of these three tools allowed us to achieve automatically the toolpath of the extrusion. And here you can see the complexity of the extruder that is being adapted for this kind of application, because the company work typically in the automotive sector or in the aerospace sector. Okay, I jump to the conclusion. I wish to thank all the guys of my laboratory, that is the Digital Fabrication Lab. Without them, it would be impossible to achieve these projects. In our laboratory, we have different machines to print steel, concrete, but also clay, raw material, or ceramic material. And you can see here how we can reach complex geometry by the combination of artificial intelligence and parametric modeling. Thank you very much. I leave you our LinkedIn profile is the profile of the laboratory. So if you wish, you can contact me if you have question or you wish to start a collaboration. Thank you very much.
Thank you very much, Professor Valentino, for your interesting presentation. Let's proceed. We go further. We go to Professor Sandra, and I know that we have several questions here in the chat, but we will wait for the end, okay? And we discuss all together. So Professor Sandra is Associate Professor in Autonomous Manufacturing of Construction Materials in the research group Concrete Structures at EU Eindhoven. And today, Professor Sandra will talk about additive manufacturing of smart and sustainable concrete, state of the art and challenges. So, Professor Sandra, you can start whenever you want. Thank you very much.
Can you hear me?
Yeah.
Yes, and I believe you can see the presentation, right?
Yes.
You're seeing the right one. Okay.
He's not,
because
he's not in full screen yet. Okay.
Sorry?
He's not yet in full screen.
Ah, okay, because that's my problem when I share with, okay, so I'm going to see if I can share the right one, because that's the problem. So let me see where I can, okay, this is always a bit messy.
Yeah,
So can I stop? Yeah, but now I cannot stop the sharing. So, oh, okay, this is annoying because I can't find it. Okay, it's here, stop sharing. So I'm going to make it full screen before, and hopefully after that, I should be able to share the screen. Okay, so I'll do it again. This time, I think I have the right one. So let me see if I can share. So do you see the right presentation?
Yeah, thank you very much.
You see the full screen. Okay,
yeah.
Perfect. Okay, so first of all, thank you very much for inviting me and for the really nice webinar so far and the presentations that are very interesting. So my presentation today, I'm going to show you also a little bit of the work we have done so far at UE with my research group. And also the next steps. And in the next steps, I'm going to discuss a little bit the challenges and the obstacles that we're facing with especially upscaling the 3D concrete printing. So the first, just an overview from what we started with sustainability and multifunctionality. So my focus of my work was first to try and increase sustainability in the mixes that we use for 3D concrete printing, and also combine it with functionalities, because this comes from my previous research with self-sensing, self-cleaning, and other special smart materials, let's call it this way. And then we move to the process control, because we felt the need to start controlling the process more, because we realized that there were a lot of problems with, especially when we moved to the large-scale printing. And after the process control, we moved and we're looking now into ML models, so machine learning models, AI, and digital twins. So just an overview that what the field already has is printable mortars, but most of these commercial mixes are still very Portland cement rich. So they have a very high content of clinker and Portland cement. There are maybe a few blended cements, but not so much. There's a lot of work done already in using waste and alkali activated materials, for example, also some emerging hybrid binders. But this is yet to come to the commercial side. So now, of course, the research is also moving a lot to the not just the optimization of the printability, but also to the questions about durability, thermal performance. And for example, we did a lot of work with Porto in that area of the thermal performance of 3D printed materials, but also looking into the anisotropy problems and the multifunctionality. And there's also a lot of potential in automation, and there's indeed already some control and some inline measurements, for example, being developed, but it's still in a very early stage. And what's still in our perspective here at UE is causing some problems to the full deployment of 3D concrete printing is the full control of the mixture, the properties of the fresh materials, especially when you try to reduce the clinker content, or you want to add, for example, funnel fillers. Also the properties control during pump and extrusion that connect with the residence time, the shear history, also the moisture loss. So all of these compound during the printing process and is still very difficult to control. And then we also have the part of the quality assurance. And this is also relevant to the construction industry that we need to control. We need to prove that we can provide, for example, structures that comply with Euro codes. And we have the example here that we have 3 bridges already in Eindhoven, in the Netherlands, developed, and also the houses in Eindhoven. It's still very difficult to prove to industry that we can match the same standards as traditional construction. Also, a problem that we're now facing with the ML models and AI is the fragmented aspect of the data sets. We have a lot of data now from 3D printing. There's plenty. There's really a lot that we can explore, but the data is still very fragmented. We lack data standards. It's still very difficult to develop proper models to, for example, predict printability because we lack these standards. So we began with our study through the sustainability route, using alternative binders, looking into geopolymers and circular feedstocks. We did a lot of work in that side. We developed an alkali activated composition for our printer. We work with waste, but we notice and the key scientific question that we still have to answer is how can we ensure reproducibility under the realistic conditions of 3D printing? And so how can we, for example, move to low carbon mixes, but that we can print at once? And also, how can we adjust compositions in real time or change the composition in real time? So as I said, we developed, for example, an alkali activated material for our 3D printer. And you can see here the process, but I will not go into much detail in this side. So we were able to print in a relatively large scale, but medium scale, let's call. We had good results with this material, but then we faced, of course, the obstacles of reproducibility. We also did a lot of work, and we have now a PhD student that is finishing her work on waste-derived lightweight aggregates, and we use cork for this specific purpose to develop a lightweight material. Again, we were able to print a medium scale. We printed in the final steps of the project. We printed a wall with this material, with cork, and we reached very interesting results in terms of thermal performance and also mechanical performance with this material. We moved then from looking into structural printable mortars or lightweight mortars and sustainability to the side of creating materials with functionalities. This is another side of our work here, that we try to create a self-sensing material. And the goal was to print a material that not only can fulfill the structural requirements, but that can also detect damage, or that we can develop a way that we can sense that damage and act if we detect that damage. So we printed specimens again, but this in a much smaller scale. We explored the use of graphene nanoplatelets, but then we moved to the carbon nanotubes. For the work, we managed to develop and to study the conductivity and to do it in a small scale. But we also faced, again, some problems, especially when moving to the large scale. So in this design, the different design strategies that we selected, some of the variables that we still need to monitor and we can't fully monitor. For example, when you go for alkali activated materials, there's still the open time that needs to be controlled, the pump pressure. There are some aspects with the activator sensitivity, for example, which is still a main risk. For the fillers and aggregates, you still have the segregation aspects to control, the anisotropy, the packing changes, because you have a material that doesn't always is packed in the same way. So you have changes in porosity and the extrusion stability, for example. And with the multifunctional materials or the functional materials, which we call the 4D printing, you still have a lot of problems with the mixing control. So also the pore dispersion of these materials and the cost. So then we move to the what I call the 5D printing. So trying to embed the functionality, but also the control. So the function plus the control in the system. And we took the step to improve how we control our printing process. And in that line, we have now our printing systems are capable of read already in line some properties of the material. So we can, for example, read the pressure, we have temperature, we have flowability, we can also read the water content, but we still have a lot that we need to develop and improve in this inline sensor measurements. The goal here is that we have and we develop inline measurements that we can that can help us control the material in real time, because that's what we notice that we still lack in the system. So again, another PhD student from my group is working on inline control. So we started with using a dye to trace the residence time in the material. And the goal was also to be able to print in one go, but at the same time to change material while we print. Because the purpose of 3D printing is to make construction faster, safer, and more efficient. And we think and we believe that we should also be able to change material while we print. In order to do that, you need to understand when your new material will show up in the printed part, but we need to trace it back to the mixing system. So we started by developing these inline controls, and from that work, we took some steps further to study and control other parts of the system. So we are trying to create a system that we can, for example, read the pressure and act on the material if we need to change the amount of superplasticizer, or we need to change the amount of aggregates or the amount of water. And from that process control, we realized that we're collecting a lot of data from these materials. And then we move to explore how can we use machine learning models and AI to control the materials. We have some results already from some early work done by students in my group. But what we realized is that, for example, in order to predict printability, because that's one of the aspects that we started to explore if we could use these models and AI to predict, for example, the printability of our material. So the moment we go to the printing system with a certain composition, we should be able to know already that that composition is a printable composition or not. And this connects with the fact that we're trying to use alternative binders, so more sustainable mixes, but at the same time, if we reduce the amount of cement, then we have problems controlling these materials, and we need to predict if that composition with that specific materials will be printable. And in a preliminary study, we realized, for example, that indeed the composition of the materials has huge impact in how the system and how the models will predict printability. They will say if the mix is printable or not. So we faced some bottlenecks in the study, and we faced some problems in the study. And one of them is also the non-standardized way that people collect data. So we realized that in order to really make use of these models and really make use of all the data that is being collected in different laboratories across the world, we need to work on standardizing that data. We are doing that work here in our lab. So we have already some benchmark developed to standardize data, but it's still that's still also inconsistent even within our group. There's also barriers, for example, that connect with the type of equipment that people use. So we noticed that if you use a different pump or a different mixing system, then of course the data you collect will be different, and in some way you might face some problems to then feed the model with that data. So essentially, the take-home point at this stage is that we need data governance, and we need some protocol harmonization, and some also prerequisites that we can transfer across machines and across laboratories. Because there are plenty of laboratories now that they say, oh, we are working with machine learning models, and we are working with AI, and we have our own standards for data. But then when you come to standardize across machines and laboratories, then some challenges show up. So our goal now is also to work on with digital twins. At TUE, we have now a big platform for the digital twins in education. So we are trying also to collect and organize ourselves in the different departments and different groups that all are working with digital twins. And we are connected now with that framework for the digital twins at TUE. And our goal with digital twins is not just to make the digital twin of the machine, because that's not, that's relatively simple, so to say. But then when you try to couple material evolution and the process state, then if you go to a real digital twin that updates in real time, then we still face all these challenges. That, for example, in the materials layer, we have the binder chemistry, we have the presence of additives and aggregates. In the machine and process, the layer pump, then the sensing layer. So all of this, we are now in the process of starting to develop a digital twin of our system, but is still it's a big task and a challenge. So the open challenges, the open challenges that we now face to really make this system, the 3D concrete printing, a smart and sustainable solution for construction, is first to have robust, printable, low clinker materials compositions, because we still depend a lot on the variability of these raw materials. And that's a challenge. We have the challenge of properly disperse and the long-term stability, for example, when you use nanomaterials, and also to understand the microstructure. So we need more inline information, so real-time information about, for example, the microstructure of materials, the porosity of these materials, even in the fresh state. Then we have the measurement and control, where still lack inline measurement and inline information, so real-time information that can inform us about the weight and the conditions of the material. And that all of that, so in the layer of the AI and digital twins, we still face some challenges with, for example, the data standards, and especially across machines and labs, and also how to generalize the models. If you shift domains, for example, or how to deal when you have small data sets, that's something that we still cannot overcome. And also the hybrid physics, for example, of these compositions, and how to introduce that physics-informed part in the ML models. So to summarize in a take-home message that I tried to come up with one, so I think that to really reach a robust deployment of large-scale printing, we still need a lot of work, and a lot of work needs to be done in the inline sensing, in my opinion, also in the ML models and the digital twins, but also in the material side, so that you can properly scale up the materials you develop in the lab. So thank you. This is a short overview of our lab and our challenges. And now, yeah, up to you again, Anna.
Thank you, Sandra. Thank you very much for your nice presentation. So as we are doing still, we will wait for the end for the questions and answers. So let's move on to Professor Barbara Rangel. Barbara is an architect, an assistant professor at Civil Engineering Department here in Faculty of Engineering, University of Porto. And Barbara will talk today about finding the design of 3D printing in DigiFilp Lab. So Barbara, the floor is yours. Thank you very much.
Hi, everybody. Thank you for the invitation, and thank you for the other speakers. The presentations have been really interesting. I'll start sharing the presentation here. I think it's now. Is it working?
Not yet in full screen. We see, but not yet in full screen.
And now?
Yes, perfect. Thank you.
Okay. So first of all, I would like to say that the work that we are presenting here is made by a set of people, some of them included here in the presentations today, like Ana Sofia, Jorge Lino, Manuel Jesus, and all the others. And this is part of a huge group, of an integrated disciplinary group, where we have the luck to be working in different areas, and we learn a lot with each other and make possible to grow our knowledge on the 3D printing. So that's the first thing. This is not my work, this is our work. The work that we are presenting now, it's more related with an experience that me and Jaime Cunha, one of the persons that's working in this group, made during the last year. Me and Jaime, we are architects working with civil engineer issues, and we were concerned and had a mystery to understand how does the building systems can make different design tectonics, meaning different forms and different languages in architecture. And that's been my research in the last decades of my areas of research in between architect and engineer. So if we take a fast look in the history of the construction, the history of architecture, and the history of civil engineer, we can understand that the way we build is directly related with the form of architecture. So the question that we make now, how come does 3D printing will transform or is transforming the way that we can make architecture? If we look at Corbusier's experiences in La Unité d'Habitation de Marseille, when the concrete was beginning to be used, complex forms started to be done. Or even in Frank Lloyd Wright, experiences in this falling water house, the possibility of having spans was used in a very intelligent and robust way to define the architecture of this house. And of course, Sagrada Familia, it's an experience of disruptive construction and architecture. I could imagine if Gaudi was born in our era, if he had a 3D printer, I can imagine he would have gone even further with his experiences, his formal experiences. And Miguel Fisac, an architect and engineer from Spain, where in his work he was always making this relation, this biomimicry relation between the human body and engineer. And today, with the possibility of the digital design, the parametric design, and all these possibilities, it has been easier but tricky at the same way to bring the ideas that start with a sketch with a pencil and a paper to the reality, as you can see in this Olympic stadium designed by Herzog and de Meuron. So now, the question that we put at DG at FEOP is, what can we do more with the 3D printing in terms of architecture, but even in terms of engineer? What can we do to decrease the CO2 emissions, not only with the reduction of time and material, but also within the material itself? What can we do more? We have a set of students and researchers working with us on these issues, some more related with the building physics that are more coordinated by Anna Sofia, and me. I work more in these issues among the integrated project design issues and the architectural design. For instance, João Teixeira, that just finished his PhD, is just waiting for the final presentation. He, in his course, or in his research during the last years, he made a library of materials that can be added in the mixture to reduce not only the cement, but trying to take part of the all natural aggregates of the mixtures, and with that give the possibility of new tectonic forms, not only in the texture, but also in the color, using waste materials as brick from demolitions, glass, and also some stone powders like granite or marble. This is related with the parametric library that he developed, so that we can who uses his research can make the direct connection to in the development of the piece with the characteristics not only of the material but also with the equipment. Elis Ribeiro, also working with us in his PhD at DG at FEOP, she used marble powder to develop some Kobogo structures. That this is a structure that is used in Latin American countries to make the natural ventilation of the spaces. And now she's also developing a wider structure like this, but using fibers in the mixture. We also were able to produce some research on using soil as the main component of the mixture in the work of Ana Luisa Guimarães, student of Master on Design that we have also in the Faculty of Engineering. The work of Sofia Pessoa, directed by Ana Sofia, and Sandra Lucas. She has been working and continues now after her PhD is finished in the study of the thermal behavior of the 3D printing system. Tasia is making the connection of the thermal behavior of the wall and its parametric geometry. and Jaime Cunha made an LCA study of a house printed by a company that we have been working with that is here in Porto. And also Manel Jesus, that will present later, is taking or studying the use of 3D printing in the refurbishment of monumental buildings. And also here a work made by ILS, directed by Jorge Lino, and that is working on 3D printing in reefs. This is another work that we have been also working and has been developing in a scientific project, but also in the PhD project of Juan, that we are developing a building system with soil, and also some experiences that we made with our students in the Master of Integrated Project Design in Construction, where we work directly with the companies, and we ask the students to think in an evaluative house that could be printed within a table of 12 by 12 meters. That's the possibility of the printer that the company have. With all these experiences, we were invited by this company, Havlar, to make scientific support of their work. And we made a competition with them in Matosinhos, it's a city next to Porto, to make a project for a municipal building where is a lab of circularity, and the community can go there to upgrade their supplies and learn a bit about the circularity in their community. We have the lucky to won that competition, and that was a real hands-on work where we could put in practice what we were working on, the industrialization of construction from A to Z, meaning we were able to use the construction, the 3D printing construction on site by printing the main walls, but also we made a prefabrication study where all the elements that were not printed were made off-site, and we studied how would we arrange and articulate these two ways of building to reduce the time of construction and also to reduce the amount of waste produced in the construction. So the on-site work was mainly the work made in the terrain, and also the walls, the printed walls, and all the rest, like the structure inside, the windows and roofs, and of course all the other sets of doors and bathrooms and stuff were all made off-site. It was very interesting the way that we work, because it was as we were thinking in an industrialized mindset, we had to make a very detailed thinking in all the elements that were going to the site, because there was no time for changes, and it would be difficult to make to correct errors. So this was as I said, a way of thinking in an industrial mindset that we are not very used in the construction processes, because I don't know in other countries, but in Portugal, the construction sector is still very, very conservative, I could say, and the coordination of work and all the management of work is still very, I would say, difficult to gather and articulate timings and tasks in a proper and very optimized way. So we had all this preoccupation of having all details very studied and all the timings very studied because of the time of the printing, for example. So all the elements that were not printed, what I was saying before, were made outside the building site. For example, the bathrooms were made in these infrastructured walls and all prepared in the factory before they went to the building site, so that when they arrived, we just had to make like a plug and play construction to make it fast. So this kind of process put us a lot of challenges, and particularly in the timings of articulating the different elements. For instance, the windows and the walls. So we had to make in the factory some experiences to articulate, in this case, for example, how could we put the base of a window without stopping the printing system, the printing process, like in the latest presentations that were made here from Vittorio. We know that we have a cold joint when we stop the printing, so we were worried about those issues. So we had this preoccupation of how could we manage the construction and have at the same time having the possibility of not stopping the printing to put all these elements. So a set of tests were made in a factory of the main walls, of the doors, of the structures that we wanted to do, for example, to disguise this steel column that we have in the middle of the building. So we tested it before we went to the building site, making these small prototypes. For instance, the texture of the wall, the way that we could use the printing to make different forms, to introduce the lightening, for example, or to understand what would happen in those cold joints after printing in 2 days. Here are some tests that we made concerning the introduction of the windows. That's a big problem in the 3D printing construction, because we are putting two systems with a really different tolerance. We have a tolerance of the 3D printing of centimeters, and then we have in a window made by steel and glass of a tolerance of millimeters. And these the connection of these two processes and building elements can be a real problem after in the performance of the building concerning water entrance or even humidity and thermal joints. So this has been a real problem for us. So the construction of these prototypes were essential to think and to provide solutions to the construction itself during the system. Also, during this first phase, we thought in structures that could help us not only to be aware of the thermal bridges and break the thermal bridges, but also to facilitate after the setting of the window systems that were once again made in the factory and then after put in the building site. So we developed these kind of beams that were already prepared to receive the window structure, and having this void in the middle to make possible the break of the thermal bridge. And at the same time, we had or we tried to just have this only cold joint, making the stop of the printing system, to put all these supports for the doors and windows. So this came as a design principle and to be added in our method that we are developing, because it would be important in terms of construction to make just one stop during the printing system to avoid those cold joints that Vittorio was saying. So we tried to design all the building just with this same height. Also, in the design of the wall, another concern that we were worried about was the size of the wall. These walls, they have 12 meters long. So talking with the structure engineers that helped us to develop this building, we thought it would be important to have a curved form in these main walls, also because of the stability of the wall. So that's another lesson that we got from the construction possibility of having a real building to have this experience. So when we talk about the freedom of the 3D printing, it's very limited. If I can say it is opposition of concepts. So, but that in the end is limitation of having these added texture that we were not thinking in the beginning. I think it gave personality to the building itself, taking a part of the design these problem, saying problems was a solution and a statical solution for the building. These are some images of the building almost ready, and here it's very obvious the thing that I was just telling now, where we can see the plan parts are related with the column behind, and then the curved parts where we have a void and after. The building is divided in 3 blocks because of the size of the printer. Each block has 12 by 11 meters, and then in between them we have a metal structure that makes the foyer of the old building. In here we see the curve that I was referring, and the paint that we put in the cold joints to try to avoid the cracks in between the layers. It was also interesting to make this work as we know, we in Europe don't have the regulations to use the 3D printing as structure. We are obliged to have a structure inside the wall. And in this project, we decided to use metal structures so that we could make it off-site and easily put it inside the wall. We were very worried about, again, the tolerance, because we don't know and we don't have access to the inside of the wall to make sure that the column goes down perfectly without any interruption. But when the structure came to the building site, and in 3 hours the structure was mounted. And it was interesting to understand that while the first building after the first building was printed, it was 2 days after it was possible to put the 1 day after it was possible to put the structure inside, and while the other two were being printed. During the printing, the first lines, we had in mind these issues, so we left these small windows to make possible to screw the column to the slab that you can see here in the last photograph, and some sketches where we were studying with the team that was making the printing of the walls, how would it be easier for them to work with these issues. And as you can see, during the printing, we just had 4 persons two in the pumping machine and 2 controlling the printing, the head of the printer, and putting these metal wires just to make sure that the 2 parts of the wall are completely parallel. And here you can see I think this is a video, yeah. And here you can see that's not working. Good. Sorry about it. But anyway, that you will see, we'll have a building in the middle. And here you can see the structure of the foyer already in place, and the last building is being printed. And in the last photograph, you have the metal foil put in the structure itself. As you can see in this little video, the first building is already the structure, and the second building is starting to be printed. I think this is also a video. Here is the printing of the last building. It was also a lesson because in the only 2 days that were raining in July, we were printing. So it was interesting to to have the most warm days of July and also the most rainy days of July in the printing. So that was also a lesson. Sorry. And here the team very happy when they finished the first building printed in here. This was also a challenge because while we were printing, we had to wet the material, and during the printing, our team, in this case, Jaime Cunha and Sofia, they went to the building site, so we were always there making sure that we could collect information and data to study these issues in our next projects. And they put a sensor inside the wall, and we now are collecting data for these first years, so we can understand with the eyes of the building physics how is this building the performance of this building during these seasons, so that we can start thinking of making a digital twin and make the prediction of this system. How can we improve it, and how is it going to be performing in other projects that we want to do? One thing I think I forgot to say is inside of the walls, we put cork, black cork inside to provide the thermal insulation. But we are also thinking in other possibilities to make the installation. Some images of the building. after the printing and starting to put all the other sets like the air conditioning, the electrical supplies, and also the interior doors that were made in the factory, and we try to make like these boxes to be easily put in the walls. And here's some images of the image itself, the infrastructured walls that I've told you about that were made in the factory and put inside the bathrooms so that it would be an easy plug and play system. Here's some finishings almost ready, and the exterior finishings where we tried to put materials that were easily the water could go to the ground. Here, sorry, there was a video missing, but here's some also in the outside of the building. We used a system and finishings that permitted that the rainwater could go directly to the ground instead of having a water system blocked, and make it also the water collection, make it also circular and also part of the whole concept of the building that was making the CO2 emissions lower. And now we are making the LCA of the whole construction set, just to understand if what we predict was accomplished and what can be optimized in the following works that the company and us could make. And that's all. Thank you.
Thank you, Barbara. Let's move on to not is the last but not the least, Manuel Jesus. Manuel Jesus is almost finishing the PhD here at FEUP, supervised by me, by Barbara, and by George. So we are here as a team. And today, Manuel will talk about a paper that was published in Buildings. That is the optimization of 3D printable cement and lime-based mortars for building heritage rehabilitation. So thank you very much, Manuel, and the floor is yours.
Can you see my screen?
Yes, perfect, Manuel.
Well, good morning, everyone. First of all, thank you for the invitation. I hope you are enjoying this webinar. My name is Manuel Jesus, and I'm a PhD student at the University of Porto, as Professor Ana Sofia said. And I'm going to present a study that we conducted, and it's within the scope of my PhD thesis. So this presentation follows more or less the structure of our paper recently published in the Buildings Journal. So first we'll take a look at the background and the goals of the study. Then we'll dive into the experimental work and the methodology followed. And finally, I'll share some results and the key takeaways from our research. So first of all, it is known that cultural heritage buildings are vital for preserving the identity and history of their own location. And sometimes this preservation can be compromised by environmental damage, lack of documentation, and difficulties associated to traditional methods, which are labor-intensive, costly, and sometimes imprecise. So in this regard, 3D printing enables a precise replication of complex geometries and decorative elements by using materials like cement and lime-based mortars that are capable of providing strength for structural repairs in the case of cement, and in the case of lime, it ensures breathability, flexibility, and compatibility with the historic materials employed on these structures. So building on the framework that I've described, Here we identified a clear opportunity to integrate some advanced digital tools into the restoration of architectural heritage. So our approach uses 3D laser scanning and 3D printing to guide the recovery process. And what makes this study unique is the application of these technologies using compatible materials such as cement and lime-based mortars, ensuring that they remain faithful to the original substrates of the heritage buildings. So by merging these three distinct fields of knowledge, digital surveying, additive manufacturing, and built heritage rehabilitation, we arrive at the core topics illustrated in the middle of this diagram. So among these mortars. The case study that we chose, the San João National Theatre in Porto is classified as a national monument and was designed by architect José Marques da Silva and inaugurated in 1920. So between 2013 and 2014, conservation works on the facades were carried out by an institute in our faculty, followed by some inspections of maintenance in 2017 and 2019. So during the restoration, these elements shown here in the pictures are corbels that were replaced and were replicated using some molds. So several mortar samples were analyzed at the University of Aveiro and revealed that the corbels were made using a cement and lime-based mortar with a siliceous sand coating applied. So moving on to the experimental plan, it began with the computational modeling of the test specimen in Grasshopper. So during this stage, we designed the 3D model, choosing the layer dimensions, the printing speed, the extrusion factors, and later on the G-code was created. Then the second test focused on mortars preparation, and this involved the characterization of the constituents, the determination of the dosages, the mixing times, and the speed. Also, environmental conditions like air temperature and relative humidity were strictly controlled throughout this phase. So once the mortar was mixed, we performed the fresh state characterization through flow table tests to pre-evaluate fluidity, while some slump tests were used to assess the material's initial buildability. If the mixture in this phase presented adequate consistency, we proceeded to the printing trials to evaluate other printing parameters that were talked about in other presentations here, like extrudability, buildability, and flowability. Finally, standardized tests for hardened state testing, and this included flexural, compressive strength, and capillary water absorption tests to evaluate the durability of the mortars that we developed. So regarding the equipment that we used and that we have available in our laboratory, we began with the experimental campaign by defining the operational parameters. So a Delta WASP 4100 was used, and it imposes some specific material constraints. So since the nozzle diameters are quite small, we have two nozzle diameters of 6 and 8 millimeters, the maximum aggregate size is limited to 1 millimeter. So this required a higher concentration of fines in the mixture design to prevent the clogging of the extruder. Regarding the printing volume, the system is limited to a 40 centimeter diameter to a 1 meter tall element. And the printing speed is kept at 200 millimeters per second, and based the available nozzle sizes, the layer height must be maintained between 2 and 4 millimeters to ensure optimal deposition and interlayer adhesion. So regarding the 3D model design, the printing path was programmed in Grasshopper, as I said, and translated into G-code using the Termit plugin, which is optimized for Delta Wasp printers. So the test geometry was designed to evaluate material behavior across different levels of geometric complexity, as you can see on the figure on the right. And the samples were printed to height of 50 millimeters, consisting of 20 layers. While the standard layer height was 2.5 millimeters, the initial layer was adjusted to 3 millimeters to mitigate the material spread and ensure a stable base for the subsequent layers. Regarding the mix design, initially we defined two primary mortar formulations based on different binder to aggregate ratios. So the first one had 70% of binders and 30% of aggregates, and the second one had 60% of binders and 40% of aggregates. For each ratio, we tested 3 different binder combinations, resulting on 6 base formulations without superplasticizers. So from this first set of trials, the best compositions were selected for an optimization using superplasticizers. As aggregate, fine sand with 1 millimeter diameter was used. And to ensure consistency throughout the experimental campaign, a fixed quantity of 1 kilogram of dry mixture was prepared for each trial. So regarding the mix process and the fresh state tests, a strict mixing protocol was followed that began with the accurate weighing of all constituents. First, the dry materials were blended on a mixer at low speed to ensure an homogeneous distribution and to prevent segregation. We then gradually added water over a 90-second period while increasing the mixer speed over time. And to guarantee the full incorporation of all the components, we paused to scrape the mixing bucket and the pedal before a final 2.5-minute mix. At this stage, fresh state characterization was conducted, namely the slump and flow table tests regarding EN standard. And finally, the mortar received another quick remix to maintain its consistency before being loaded into the extruder cone and printed. So before the final prints were initiated, the printing parameters were calibrated during preliminary testing. So the first priority here was to optimize extrudability achieved by balancing the printing speed and the extrusion factor. So as shown on the figure on the left, interruptions in filament resulted from nozzle clogging. So these failures were attributed to an insufficient extrusion factor, excessive printing speed, or even a lack of water in the mortar, which prevented consistent material flow. On the other hand, when the extrusion factor was set too high or the printing speed was too low, often combined with a high water to binder ratio, the layers suffered structural failure. So this was identified as plastic collapse or elastic buckling, both of which served as indicators of pure buildability. So to avoid the structural failures previously discussed, the printing parameters had to be standardized and are presented on the table on the left. So using 8 millimeter nozzle and a speed of 40 millimeters per second, each specimen was printed in about 5 minutes, and a layer height of 2.5 millimeters and a width of 10 to 50 millimeters was achieved, and these settings provided the stability needed to prevent plastic collapse or nozzle clogging observed during the initial calibration phase. And to ensure a consistent and objective evaluation of the printing trials, we also established a qualitative scoring system, as you see on the table on the right, based on 5 indicators: finishing, layer dimensions, structural integrity, printability, and collapse. Each criterion was rated on a scale from 1 to 5, where 1 was very poor and 5 was very good. And the final result was achieved with the arithmetic average of each formulation. So the table on the left summarizes the experimental results and the dosage used for each mortar produced without superplasticizer. And to control the properties of the fresh mortar and to determine the necessary water content, we calculated the water to binder ratio and the aggregate to binder ratio. So the water to binder ratio, as you can see here on the table, stayed between 0.35 to 0.40, which matches the literature that we found. So this value is largely driven by the particle size of these materials. So finer particles like cement have a higher surface area and therefore require more water to stay workable for printing. On the right, we have some pictures of the best prototype that we printed. So the best performing formulations were selected for printing trials, not this time with superplasticizer. And here, the primary objective was to enhance workability and flowability, but without increasing the water to binder ratio. So despite these optimization attempts, some formulations with higher lime content proved unsuitable and therefore were excluded. The resulting water to binder ratio for these mortars ranged between 0.29 to 0.34, and once again they were consistent with the established literature. The superplasticizer here was added at a dosage of 0.5% of binder mass. And while this admixture allowed for a significant reduction in water content, these mixtures experienced a faster loss of workability, in this case, a reduced open time. So this rapid stiffening presented a technical challenge because it increased the risk of extruder clogging, and some interruptions during the printing process were obtainable. Now I have some videos here to show all the printing trials. On the left, the 3D model that we developed and I talked about. And here on the right, the application to the corbel of the theater. The corbel was scanned and then modeled also in Rhino and Grasshopper and converted into G-code. So, compressive and flexible strength tests were conducted in accordance to EN standards also. And to evaluate the durability, as I said, the capillary water absorption coefficient was determined follow an ISO standard, measuring the mass of water absorbed per unit area over time. So the experimental results show that the flow ranged between 201 millimeters to 220 millimeters, which aligns again closely to the literature, as you see on the graphic on the left. So the slump test result presented values between 10 millimeters and 20 millimeters, which fall also within the acceptable limit. So these values indicate satisfactory shape retention, a critical indicator for high buildability. And as you can see, formulation 3.1 and 4.2 recorded the lowest slump, demonstrating superior cohesion and structural resistance that is required for high-performance 3D printing. Now, regarding the water absorption by capillarity. This test was conducted over a 24-hour period to evaluate the water infiltration on each composition. As established in the literature, the hydric performance of mortars is closely linked to their porosity, influenced by binder content, aggregate grading, and the water-to-binder ratio. So among the mixtures without superplasticizers, formulation 3.1 demonstrated the lower water absorption coefficient, and this indicates a denser and less porous matrix attributed to its higher cement content that facilitates a more cohesive and compact structure. The inclusion of superplasticizers allowed for a significant reduction in the water-to-binder ratio, as I previously said, increasing the matrix porosity. All the mixtures with superplasticizer exhibited substantial lower absorption coefficients in comparison with their counterparts, with reduction percentages ranging from 45% to 67%. Now, following the fresh state evaluation, only the best mortars were selected for hardened state testing, and this result confirmed a direct correlation between cement content and compressive strength. For formulations 2.1 and 6.3 with more cement achieved strength of 54 megapascal and 62 megapascal, which are notably high for 3D printed mortars. As expected, formulations with less cement of 60% show a decrease in performance, presenting values at around 49 megapascal. The addition of superplasticizers outperformed the base mixtures because by reducing the water to cement ratio, the porosity was decreased and the material density was increased, leading to the highest overall mechanic performance in series 3 and 6. On the table on the right, and consistent with the compressive strength findings, the flexural strength values for mortars without superplasticizers were also observed in formulations 3.1 and 6.3, which reached 7 megapascal and 7.4. This result confirmed that high cement content is a primary driver for the flexural performance. While the addition of superplasticizers enhanced these values, a notable exception occurred in formulations 5.5 and 6.6, which exhibited a decrease in strength compared to the mortars without superplasticizer. So the conclusions that we could draw from this work are that the tested mortars met the mechanical requirements for non-structural heritage elements. The mortars with a higher cement ratio provided the best balance between mechanical strength, extrusion stability, and surface quality. The formulations with higher lime content exhibited poor shape retention. The superplasticizers improved the flowability but shortened the open time. Mixtures with lower aggregate content produced a superior finishing also and better interlayer bonding between the layers, and cement-rich mixtures offered better printing stability, while lime-rich mixtures provided a more aesthetic visual match to the historic substrate. Also, the lower water-to-binder ratios and the higher cement content minimized porosity and capillary water absorption. Thank you for your attention. I hope you enjoyed the presentation.
Thank you, Manuel. Thank you all for your presentations. I hope that was interesting for the audience. I believe so, because we have almost 29 questions. Fortunately, our speakers helped on this job and answered already 20 of those 29 questions. So we have still one again. So 10 questions here to discuss if possible. The first one, I don't know the person that the question is to whom of, I don't know, but I will, let me read. Building codes were written for wood and masonry. Are current codes a barrier to adoption, and how close are we to having international standards for printing structures? I don't know if the question was to Valentino. I know that Valentino already answered all the questions that were directly to him, but maybe Sandra can answer. I don't know.
Well, I can speak about here in the Netherlands. The limitations of the building codes don't just apply to 3D printing. So, for example, if you want to build with geopolymers here in the Netherlands, that's a problem because you don't really have a way to, for example, create structures with geopolymers, alkali activated materials. I can say that when we did the bridges, we did the Eurocode by testing. So we tested some samples, big samples from the structures, and we proved by testing that indeed those elements were complying with the Eurocode. So that's a way that you have a workaround. We have something in the Netherlands called the Beton Accord, and the Beton Accord, it's an agreement for concrete that companies that produce, that manufacture mortars and cement, and also construction companies, they made an agreement to lower the carbon footprint of concrete and the impact of construction. And they are discussing also that there are discussions about creating those standards. But I don't, as far as I see as of now, I don't see any significant progress on that side.
Okay, thank you. So another question is about what are the current physical limitations? Can we print a 20-story building today, or are we stuck at a single-story structure? I don't know, maybe. Okay, Barbara, are you here?
Yes, I'm still here. Yeah, we can 20 stories building, not yet.
Not yet.
So the direct answer will be no, we cannot. If we print a wall with 20 stories height, we can think in printing with offsite printing systems. That's the only thing that we can do. And also concerning what Sandra Lucas was just saying, as most of you probably know, in the United States, it's possible to use the 3D printing as the structural part of the building. Not yet in Europe. We are working on it, and so that's the research work that we all are making is really important to make it possible, and to show the commissions that this possibility is viable. But in Ireland, there's a company similar to Avlar, the one that we are working with. They worked with 3D printing walls as structure, using pretensioned cable inside the walls to make the structure. And also this enterprise that we are working with, Avlar, is testing that system in a work they are making it here now. So what the concept that they are using in terms of structure is making the walls as a masonry wall, considering the structure of the main concrete used in the wall composition.
Thank you,
but
Barbara.
It's able to print on site 20-story.
Another question, but this is for you, Barbara. Does 3D printing truly liberate architectural creativity, or are we simply replacing the old constraints of formwork and labor with new ones dictated by the software algorithms and material viscosity?
As we say here in Portugal, and I'm sure that will be a saying in almost of the countries, our liberty stops when the other starts. So the liberty that we have in 3D printing, for example, in that wall that I've showed you, my liberty stopped as an architect when the liberty of the concerns of the structural engineer started. So the liberty, it's the concept of liberty, it's tricky, saying that you cannot build or design a wall, a house upside down, of course. What we can do with the 3D printing that we cannot do with other systems is making the parameters of construction concerning structures, thermal behavior, and etc., part of the design system. And that's the beauty of this system, considering the physics and physical performance of the building, part of the design and the tectonic of the design. So when I read articles saying that the 3D printing offers an architectural liberty, I always laugh, because it's not a real freedom. It's restricted freedom, I would say.
Yeah, maybe a different freedom.
Yeah, yeah.
Okay, a question maybe for Sandra, if possible, about after mortar casted, at middle section of casted section cracks. Is any recommendation to solve this issue? I don't know, maybe.
Let me check the question to see if I
Yes, I don't
understand.
know.
Okay.
Probably Valentino was the right person, but I know that is not here with us.
Where is the question?
Is the
where was that? I can't see it.
Fourth one.
There's the I have one. Okay, mortar cast. Okay. After 3D concrete. Okay. Mortar casted at middle section. Crack. Okay. Well, I think that cracks because it is restrained, right? So if you have a material that is restrained on all sides or on two sides, then if there are forces that tend to pull out the material, so the material will crack. So what we need to this is something that, for example, not so much me because I'm more on the material side, but the share of my unit, my group, Theo Saleh, he has several master students already working on this issue of the cracking and the shrinkage, and that's a problem with the material. It's a reality. It has to do with the amount of cement it contains. So the more binder you have, especially cement, then the more shrinkage you will have. And also has to do with the restraint of the material. So if you can find a way not to have the material restrained, then you won't have a crack. So that's maybe you have to couple a solution that you print, because if I understand, it's a solution where you print a material and then after printing you use that material as sort of a formwork and then you cast other material there. So it's something like that. Yeah. So then it's a problem. So you need to work on the design. It's a possibility. We did it with the cork. So the final walls that we printed, we work with the design precisely not to have this restraint in the two surfaces of the wall. Or you have to work with a material and maybe work with a material that has very low shrinkage.
Okay. Another question that is a transversal question that about the connection when we are talking about bilayered walls. The question is the connection between bilayered walls seems to be placed manually and maybe not enough stiff and well anchored. So it's reliable. Like we are talking about industrialization, about automatization, and okay, what can we do in that part of the process as it is done manually? Yeah. Jorge,
Yeah, I think that as soon as technology evolves, so we have the upgrade of technology, we can have automatic systems to place these reinforcements automatically. So I think that if that is in sufficient amount, I think that the technology will solve that issues in the near future.
Okay. Another one, what about the foundation, the base, before starting the 3D printing wall or other elements? I don't know, maybe Barbara, with your experience with the house that you presented to us, can you answer this question talking about the experience you had in the way you solved the foundation base on yeah?
I would ask you to give me 5 minutes because I'm entering my car. So if you can change for the other, and then I will
Okay, no
answer
worries.
that one.
Okay, no worries. Another question about are there any interlaboratory or technical committee currently working on 3D printable? Yes, Sandra is already answering with a hair. I would be very interested in being a part of such initiatives and contributing to them to the best of my ability. So, okay, let's. You have the opportunity to connect, Sandra, if you want to ask.
Yes, yes, there are. So, and there were some tests done in an interlaboratory committee. So the committees are in. These are technical committees in RILAM. So if you know RILAM, it's the Association for. Well, it's the French name, so I don't remember exactly the name, but I can write it in the chat. So this is the.
Sandra, your
Yes,
microphone.
I just muted myself because every time I try to write an M, I mute myself. So I'm going to do it in a different way. I was trying to write RILAM. So this is a RILAM association. They have technical committees. Well, the thing is that you indeed you have to be a member of RILAM, which, for example, our department is a member of RILAM. So usually institutions, they pay to be members. So I don't know who asked the question, but if, for example, you are a PhD student or a student, you have even, I think, bachelor student, I think there's a discounted price. So there are some conditions that you can be involved. And maybe you can even be involved as an observer because you can still register with RILAM, not being a member, but you are registered. And I think that you still have access to the information. So depending on the person that asks the question, so if you check if your institution has those contacts, as far as I know, I think RILAM is probably in Europe. Currently, there's also FIB. There's another association that I know they also are connected with some work done in 3D concrete printing.
Okay. We had here a question, but is specifically for Valentino. Maybe we can put the question to Valentino later because Valentino is not anymore here with us. Barbara, are you available to answer? Because I believe that is the last question.
Yes, I'm
Okay, I will repeat. I don't know if you listening in the first place, but I can repeat the question. Is about what about the foundation base before starting the 3D printing wall or other elements? So maybe you can explain a little your experience in the house that you show us, the way that you solved the foundation.
We didn't make a linear foundation. We made a slab in the site, and we printed directly on the slab. That's what we usually do in the 3D printing buildings. So we have a straight and direct slab made in the site. In our case, we didn't put it right directly. We made like a bed of stones. I don't know the name in English. In Brita. I don't know the name in English. Maybe my engineering colleagues could help me. I can't remember the name. And then we printed directly in the bed, so we didn't make like a proper foundation. We thought in further projects that we are developing that we could afford and optimize this slab making these slabs just in the place of the walls. But then we made a calculation of time and material, and it wasn't optimized. It would take more time and more manpower to make this design of the foundations for each wall instead of making just one.
Okay, so now I have a last question that came right now. Are the 3D printing concrete buildings sustainable for Nordic climates with massive snow and wind blows, including wet conditions over half of the year, and considering that is without extra structural frame? What you have to say about this possibility to use these solutions for these specific climates? Barbara, can you?
Yeah, I can answer my part.
Yeah, of course.
What the possibility of the 3D printing, as you know, is making the parameterization of the wall geometry concerning the different climates. So I'm sure the walls couldn't be with the same design that we did here in Porto, because we have a thermal behavior of the wall completely different from the Nordic countries. But this possibility would have I'm sure ways to walk in the Nordic countries. Even Cobalt is a Danish company, and they already printed various buildings over there. And as I know, I think there were no problem concerning the weather and the snow conditions. But of course, it would have to be designed and calculated to that kind of climate.
And a last question. I believe that if you stay here more time, more questions arise. So this will be the last question, okay? So what are the maintenance issues in this 3D printing when we are comparing to conventional buildings? I don't know, maybe...
Once again, the experience that we have concerning the maintenance, we are talking about walls with rugosity and with a lot of texture. So it will be an issue of having the maintenance of the walls, I'm sure. We put a hydrophobic film in the wall, in the exterior part of the wall, and also inside the places where we have water, like bathrooms and kitchens. And for now, we didn't have problems, but I think the building is very new. It was printed last July, so I don't know, maybe in 2 or 5 years' time, we can say more about it. But that's an issue of having this texture, but also a granite wall is the same problem. Okay. But if we want a plain wall and very plain, we cannot build with 3D printing.
Okay, thank you very much. I believe that we can close the session. So as we come to the end of today's webinar, let me sincerely thank you all of our speakers for their insightful presentations and valuable contributions. Your expertise, your experience, I believe that had provided us with a deeper understanding of how 3D printing is shaping the future of the construction industry. So I would like to also extend my gratitude to all participants who joined us today. Your interest, you have lots of questions, so the engagement made this session truly mindful and enriched the discussion. So today's presentation have clearly showed that 3D printing in construction is no longer a vision of the future. We are quickly evolving reality that promotes innovation, sustainability, new possibilities in design and construction processes. So we know that we have challenges yet, but the collaboration between the academia, industry, institutions will be essential to fully unlock the potential of this technology. So I hope that this webinar has inspired new ideas, possible connections, possible collaborations among us. So let me finish saying that on behalf of this organizing team, thank you once again for your participation, for your support. I look forward to welcome you for future events and continuing this dialogue on innovation in construction. So have a wonderful day, and we hope to see you again soon. Thank you very much.
Thank you. Thank you very much, Professor
Ana,
Ana
thank
Guimarães.
you.
Thank
Obrigada.
Thank you.
Thank you very much.
Bye-bye.
Bye.
Thank
See you.
you.
Bye. See you soon.